Hi students, let us discuss about mesh and nodal analysis in this session. Before starting, I have to say one thing, that is especially BTech students. What they do is, if they know mesh analysis, they will continuously apply mesh analysis only without thinking of nodal. Okay, or some people feel that nodal analysis is better for them, okay, to solve a problem, so they will continue to solve everything in nodal only. But what we have to do, okay, we have to, just by seeing the network, we should be able to identify whether mesh is better or nodal is better, because our target is competitive exam. So in a very shortest possible time, we are supposed to get the solution. Okay, time limit. So here we have to go a bit in depth into mesh and nodal. And the next thing is, what is meant by analysis? Okay, you will get connected with load flow studies of power systems. Now, what is meant by analysis, or what are the outputs of this mesh and nodal analysis? If you see, if you have maybe n number of branches and maybe n number of nodes and b number of branches, one should be able to tell voltage across each and every element and current flowing through each and every element. That is nothing, that is the purpose of mesh or nodal analysis. Okay, or maybe whatever the element, whether it can absorb power or deliver power, we have to calculate. Now that a power absorption or delivery can be active power or reactive power, we have to say. Okay, so this is nothing but load flow studies of power systems. But why load flow studies came, though we have mesh and nodal analysis, is mesh and nodal by human brain we will solve. Okay, we will find each and every node voltage, and we will find each and every branch current, and maybe power absorbed or power delivered or active or reactive, we will be able to tell, but by using human brain. Okay, but if you think of power systems, because number of nodes or number of buses will be very high, very huge, so with our human perception, it will take years together to solve the problem, because even for a computer also, it will take hours together or days together also, okay, to give the solution. But anyway, whatever we are doing here, the purpose of mesh and nodal analysis and the purpose of load flow studies in power systems, both are same, but the approach will be different. Here by human mind interpretation we do, and in power systems we will take the help of computers. Okay, now in this, let us think of nodal analysis. Nodal analysis came from KCL, Kirchhoff's current law. Okay, and we have one more rule, that is KVL, means mesh analysis. From KVL, mesh analysis came. KCL, conservation of charge, and KVL, conservation of power or conservation of energy. Okay, now means here in KCL, if you see what KCL say, if I have many number of branches connected to a node. What is meant by node? When two or more elements are connected, okay, that connection joint point is called as node. So this is going to be node 1, for example. Okay, for this, currents entering is I1, I2 are currents entering, and I3 is leaving, I4 is leaving. Okay, now we can say that currents entering equal to currents leaving at a particular node. Our algebraic sum of currents entering at a particular node should be 0. Our algebraic sum of currents leaving at a particular node equal to 0. But I am considering algebraic sum of currents leaving at a particular node equal to 0. Okay, so if I consider algebraic sum of currents leaving at a particular node should be 0, means that my I1 is entering, means that leaving current is minus I1, and I2 is entering, means that leaving current is minus I2, and I3 is leaving, I4 is leaving, equal to 0. Algebraic sum of net currents entering at a particular node equal to 0. Okay, so one logic here, what is that? Basically, if you see the difference between active elements and passive elements, in passive elements there is a definite interrelationship between voltage and current. Because, for example, if you consider resistance, if you know voltage across resistance, you can find current flowing through resistance. Or if you know current flowing through resistance, you can find voltage across resistance, because between voltage and current interrelationship here, okay, is there. Okay, now for example, if you think of a current source, for a current source, current is known but voltage is unknown. That voltage across current source will be decided by the system connected. If you think of voltage source, voltage is known but current is unknown, because voltage is known for a voltage source but current flowing through voltage source will be decided by the system connected. Okay, so come back to here. For example, if it is a current source, if it is a current source. Is there any change in this equation? No. The I4 is the current source, I4 will come. So, application of KCL or nodal analysis is going to be direct with current sources. For example, if I have voltage source here, if I have some voltage source here, okay, so how much current will flow through voltage source? Voltage is known, but current is unknown. Current is unknown. So, means application of KCL or nodal analysis will be indirect with nodal analysis. Okay, so with voltage source. Okay, so point is very simple. I'm not saying means whenever you have current sources, easy solution will come. It is not with respect to easy or difficult, or not with respect to easy or lengthy. Okay, but I'm saying that application of KCL or nodal analysis is direct with current source because we are forming an equation with currents. Okay, now for example, means with voltage source we have to do in an indirect way. In this video only we will see. Now for example, what is KVL? If I have, for example, this, okay, and maybe this is V1, this is V2, this is V3, this is V4. Okay, if I apply KVL in this direction, okay, means previously also we made a notion like if I touch minus first, I am going to consider minus because algebraic sum of voltage rises equal to 0 in any closed path independent of path followed, or algebraic sum of voltage drops in any closed path will be 0 independent of path followed if in a closed path. Okay, or voltage rises equal to voltage drops in any closed path independent of path followed. Already we know that is nothing but KVL. Okay, now if you see, I am following algebraic sum of voltage drops in a closed path independent of path followed will be 0 because as I have taken currents leaving here, compulsorily I have to take voltage drops only here. Voltage drops only here means in duality you will understand better about this. Okay, in duality we will see about this. Now if you see here, for example, I'm going in this direction, minus to plus, minus to plus, minus to plus. In this voltage rise or drop, voltage rise, but we are thinking that voltage drop should be considered as voltage drop should be considered as positive. So voltage rise, so minus of voltage rise will become voltage drop, and plus to minus voltage drop only plus V2, and plus to minus voltage drop only plus V3, minus to plus voltage rise minus V4 equal to 0, or simply we can say that if I touch minus first, keep minus, if I touch plus first, keep plus, if I touch plus first, keep plus, if I touch minus first, keep minus. That is going to be the KVL. Okay, so conclusion is very simple. Here voltage drops are going to be considered as positive. Okay, now next thing is let us think of, for example, if this is a voltage source. Okay, if this is a voltage source of V3, voltage source of V3. Okay, voltage source of V3. Now in this application of KVL, will there be any problem? No, because voltage source value, we know voltage source value, but how much current is flowing through voltage source will be decided by the system. So the moment you are trying to apply KVL, Kirchhoff's voltage law, means that with what do you say, if you have voltage source, application of KVL with voltage source is going to be direct. I'm not saying easy, difficult. Okay, is direct. Okay, for example, if I have current source here, okay, how much will be the voltage across current source? We don't know. That will be decided by the system. So if you have current source in application of mesh analysis or KVL, means we should go in an indirect way. But application of KVL is direct with voltage source. Application of KCL is direct with current source. Application of KCL or nodal analysis will become indirect with voltage source. Application of what do you say, KVL or mesh analysis is going to be indirect with current source. Okay, now let us see about the nodal analysis or mesh analysis. Now by end of this problem you will understand better about mesh and nodal. Okay, for example, let me think of nodal analysis. Okay, all of you take this question and then try to follow. Okay, so for example, just a minute. Okay, now it's fine. Now let us think of application of nodal analysis. In nodal analysis we have to say one thing. Okay, in nodal analysis, basically nodal analysis is more generalized compared to mesh analysis, because mesh analysis can be applied to only planar networks, but nodal analysis can be applied both to planar and non-planar networks. Now let us try to understand what is meant by planar. Okay, why we will discuss the reasons soon. What is meant by planar network? In planar network means that the network that can be drawn on a plane of paper, without any crossovers, Okay, for example, if I have this network, okay, if I have crossover, is it planar network or non-planar network? It will be planar network only, because which can be drawn, in this which can be redrawn. For example, rather than writing it here, okay, rather than drawing it here, I can draw like this, no? So it will become planar. Okay, basically without crossovers, if you can draw on a plane of paper without any crossovers, that is called as planar network. Okay, so with planar network only, mesh analysis or KVL can be applied, because with planar network we can identify meshes here. Okay, of course, about mesh analysis we are going to see very soon. Okay, so we can identify meshes, but with non-planar network, for example, non-planar network means that if I have cubical structure, okay, in the sense every line is going to represent resistance or inductance or something. Okay, so the moment it is not planar, because everywhere crossovers will be there, you cannot redraw it without any crossovers. Okay, so of course this also can be drawn, because this also can be drawn this way without any crossovers. For example, if I add two more branches, maybe from front end to back end of here, maybe front end to back end of here, So in this case, without crossovers, you cannot draw that particular thing on a plane of paper, What is the problem with, for example, this is non-planar network. Okay, what is non-planar network? Means that which network cannot be drawn without any crossovers, on a plane of paper, So in this case, what will happen? For example, if you want to analyze this by applying mesh analysis. Okay, so how to apply mesh analysis? Number of meshes has to be identified. Okay, so the moment number of meshes has to be identified, means it will be very difficult for a human brain, because how to identify number of meshes or number of closed paths, you can go wrong. So mesh analysis is meant for only planar network. For example, if you think of nodal analysis can be applied equally to both planar and non-planar, because I can say that it's a node, it's one node, it's second node, it's third node, it's fourth node, fifth node, sixth node, seventh node, eighth node. Okay, so number of nodes can be identified. So nodal analysis can be applied to non-planar networks also. Okay, so anyway, nodal analysis is a bit more generalized, because it can be applied to non-planar networks also. Now anyway, about planar and non-planar is over. Now what is meant by nodal analysis? Okay, in nodal analysis, for example, if I have one branch like this, for example, okay, if I have one network like this, this junction point, one network like this. Okay, what we are about to do is, one node we are going to take it as a reference node, because in saying the voltage, always the reference should be there, because voltage should be described with polarities. For example, if I consider this as a reference node, okay, actually some textbooks and some faculties say that this should be connected to earth potential. No, earth potential can be different and this particular potential can be different, but this is reference node. If I feel with respect to this is V1, with respect to this is V2, with respect to this is V3, with respect to this is V4. Now if I can apply KCL here, If I apply KCL here, if I apply KCL here, if I apply KCL here, then what will happen? You are going to get, in the name of V1, V2, V3, V4, you are going to get 4 equations because you are applying KCL 4 times. With those 4 equations, you will be able to find, because 4 equations, 4 unknowns. So you will be able to find V1, V2, V3, V4. The moment you find V1, V2, V3, V4, for example, if I want to know how much is the, because what is meant by analysis, each and every branch voltage I should be able to say, each and every current flowing through the branch I should know. For example, means if I want to know voltage across this, how much is this? V2 minus V1, V3. Because with respect to this is at V3, with respect to the same node it is V2. So how much will be the voltage across this branch element is going to V2 minus V3. Okay, for example, if I want to know current flowing through it, for example, if it is passive element of resistance, for example, then V2 minus V3 by resistance will give you current entering here. Okay, so I'll be able to find out current, I'll be able to find out voltage across each and every branch, such that power can be calculated and all remaining things can be calculated. Means analysis is done. Now, which node should be taken as reference node? So for example, if I take this as a reference node, try to observe coolly. Okay, for example, if I take this as a reference node, how many equations are getting? We are getting 4 equations. Out of these 4 equations, let us consider this. Okay, here in writing the KCL equation for the fourth node, how many variables will come? Current leaving through this plus current leaving through this plus current leaving through this plus current leaving through this is going to be 0. Means that how many in one equation, how many terms are coming? 4 terms are coming. For example, if I take this as a reference node, okay, if I take, for example, if I take this as the reference node, then how many equations again? Same, maybe V1, V2, V3, V4. Again 4 times you have to apply KCL, but at each and every node, only in writing the KCL, only 3 terms will come. Okay, because I want maybe current flowing through this plus current flowing through this plus current flowing through this, or current flowing through this plus current flowing through this, current flowing through this. Everywhere you are going to get 3 terms only in each equation. So which node should be taken as reference node? To that node means whatever may be the node to which maximum number of connections are there, we are going to take that node as reference node. Because one term will be reduced. If I take this as a reference node, in applying KCL here, 4 terms will come, 4 currents will come. But if I take this as a reference node, one term is going to be reduced. Okay, so reference node, very simple. Reference node in the sense, we have to take one node as a reference node to which maximum number of connections present. Okay, now I'm not saying such a big question will come in GATE exam. Okay, but in order to know, actually our flow will be like this. First I will start with nodal by considering all current sources. Then in the next step I will convert into gradually voltage sources. Okay, then you will come to know how to apply nodal analysis with voltage source also, kind of super node or something like that. Okay, now after that gradually I will convert complete sources into voltage sources. Okay, then I am going to apply KVL, because application of KVL is easy with voltage sources. For example, let me tell you here. Okay, so for example, this is a network I have taken previously. With this network, which network I have taken? This particular network is containing all current sources only, in which application of KCL is KCL, current law. Okay, so currents are known for the sources, so application of nodal analysis will be direct. Then gradually I will convert maybe this node into voltage source, this node into voltage source, this node into voltage source, this node into voltage source. Then complete network will become with voltage sources, for which application of mesh analysis will be direct. Okay, then from mesh analysis again I will come back to nodal, such that we are going to start from nodal and gradually we will enter into mesh, and again from mesh we will come back to nodal analysis, such that we will be able to merge mesh and nodal analysis properly. After that we will solve problems. Okay, now let us see here. Okay, in this network how to analyze with KCL or nodal analysis. Okay, so this is nodal analysis. Okay, now for our future reference, because I need to have one copy here, I need to have the same copy here. Okay, keep it there, enough. Now let us try to apply KVL here. For example, means what are the, which node should be taken as reference node, to which maximum number of connections are there. So let me consider this as, let me consider this as reference node. Now let me think of this as V1, V2, V3, V4, 4 nodes. Okay, I am going to write equations only. I am not going to solve 4 by 4 matrix. Okay, I will tell you how to write the equation. That will be more than sufficient, because from mathematics and all, you know how to find out, because in GATE ESE 4 variables is actually very rare to come. In order to understand the concept only, we are taking this. Okay, now for example, let me apply KVL here. What did I say? Currents leaving at a particular node should be taken as positive. So current entering in this direction is how much? Current leaving plus current leaving plus current leaving equal to 0. Okay, so how much is current leaving? Already we know 3 amperes, direct application. So 3 plus current leaving is how much? With respect to reference node, as I told you previously, for a passive elements, both current and voltages are interrelated properly. Perfect interrelation will be there. So for example, this is reference node. With respect to this, I got voltage of V1 here. Okay, with respect to this, I got voltage of V1 here. What does it mean? How much current will flow here? For example, this resistance is 2 ohm. This is the reference node. Okay, sorry, I should not write this. This is the reference node. Okay, and this is V1. What does it mean? With respect to reference, this is the higher potential of V1. How much current is going to enter in this direction? V1 divided by 2 ohm, voltage divided by resistance. So how much current is leaving here? V1 reference, V1 by 2. V1 by 2. Okay, how much current is leaving in this direction? Current leaving in this direction is going to be, see here, current should leave in this direction, means that positive should be here, negative should be here. Forget about Vx, we will come to know later. Okay, current leaving in this direction, current should enter into positive terminal for passivation convention. So current leaving in this direction means voltage should be known, divided by that resistance value. Okay, so how much is voltage? V1 minus V4. So plus V1 minus V4 divided by, how much is this resistance value? 2, 3, 4, 5, 6, 7, 8. So it should be 1 ohm. Okay, I forgot to place it. Okay, now for example, V1 minus V4, current leaving divided by 1 is going to be 0. This is the first equation I got. Okay, now second equation is, try to apply at V2. Now current leaving in this direction is how much? Minus 3. Because application of KCL is going to be direct for current source, and current leaving in this direction is going to be V2 reference, so plus V2 by 5. Okay, current leaving in this direction is going to be 8Vx, so plus 8Vx equal to 0 is the second equation. In this, what is Vx? Because it is voltage controlled current source. Okay, so voltage controlled current source, how much is the controlling variable? Where is the controlling variable? Controlling variable is here, that is Vx. How much is Vx? Plus is here, minus is here, so Vx equal to V4 minus V1. So V4 minus V1. If you place it here, so in the name of V1, V2, V3, V4, we are going to get equation. Now let us try to apply here. Okay, current leaving in this direction is going to be minus 8Vx. Current leaving in this direction is plus 7 amperes. Amperes is not required. Okay, 7. Okay, so current leaving in this direction is 7. Current leaving in this direction is going to be, current leaving in this direction means that this should be upper potential, this should be lower potential, such that my current is entering into positive terminal. Okay, so V3 minus V4 by 6. So it is going to be plus V3 minus V4 by 6 equal to 0 is going to be third. Okay, now let us try to apply KCL for the fourth. for the fourth. Okay, so current leaving in this direction, is V4 minus V1 by 1. Okay, so V4 minus V1 by 1, okay, is going to be current leaving in this direction. Current leaving in this direction is plus 4ix, so plus 4ix, and current leaving in this direction is going to be V4 minus V3 by 6, because V4 minus V3 will give you plus here minus here, current entering in this direction. Okay, so V4 minus V3 by 6 plus V4 minus V3 by 6 is going to be 0, is the fourth equation. But what is Ix value here? What is Ix? Where is Ix? Ix is here. Okay, controlling variable, because it is a current controlled current source. Now how much is Ix now? Current flowing in this direction. How much is that? V1 divided by 2, because this is reference, so V1 divided by 2. So Ix is going to be V1 divided by 2. So 4 equations, 4 unknowns. You have to place Vx here, you have to place Ix here. So 4 equations, 4 unknowns. We can solve V1, V2, V3, V4. But try to remember one thing, how much difficulty we had, because in solving these many equations, it takes much time. Okay, now next thing is let us see the same network. Let me consider. Okay, so the same network let me consider, and let us see same network let me consider. Okay, so if I consider same network, and this is 1 ohm, just a minute. Yes, okay, so this is 1 ohm, previously forgot to write. Okay, with the same network, let me change one thing, 2 voltage source. What is that? Maybe let me erase this. Okay, let me connect 7 volts voltage source to here, plus minus 7 volts. Okay, now let us try to analyze. Now in future also we are going to use the same network, so let me have a copy of it. You please take this network. Okay, now let us see how we can do this problem. Okay, so let me push it a bit more. Now come back to previous. Okay, now let us try to apply nodal analysis to this. Okay, because application of KCL is going to be indirect with voltage source, and that too, which node should be taken as a reference node? As usual, maximum number of connections are there here, so this is going to be reference node. Okay, means we can consider maybe V1, V2, V3, V4. Okay, application of KCL will not change in V1, V2. For example, V1. Okay, let me write rapidly. Current leaving in this direction is going to V1 minus V4 by 1. So V1 minus V4 by 1. Okay, current leaving in this direction is going to plus V1 by 2. Current leaving in this direction is plus 3 equal to 0. First equation. And at second, current leaving in this direction is minus 3. Plus current leaving in this direction is plus V2 by 5. Plus current leaving in this direction is 8Vx equal to 0. How much is Vx? Controlling variable. Vx is nothing but V4 minus V1. Okay. So V4 minus V1. Now at node 3, focus here. At node 3, let me apply KVL. Okay, current leaving in this direction is going to be how much? V3 minus V4 by 6. So V3 minus V4 by 6 plus current leaving in this direction is minus 8Vx. Okay, plus current leaving in this direction is how much? We don't know. Why? Because it's a voltage source. For a voltage source, voltage is known, but current is unknown. It can inject any amount of current. Okay, so what to do? Basically, why we are doing all this? In order to find out the voltage. Okay, already voltage source is there, no? Okay, whatever will be the current, because if you think of these, what do you say, unknown variables, all unknown variables are in terms of voltages. For example, if I consider here voltage V3 equal to, this is reference minus 7 volts. Okay, with respect to this is going to be minus 7 volts. So the moment any voltage source is connected with respect to reference node, you need not apply KCL at all. Directly write V3 equal to minus 7 volts. Number of, what do you say, equations are reduced by 1 or not? Yes. So is it better or not to have a voltage source connected with reference to non-reference or not? Yes. Because I need not apply KCL here at all. Okay, so number of equations are getting reduced. So though application of KCL is indirect, with voltage source, but it is easy now. Gradually you will come to know with other things also. Anyway, fourth node. Okay, fourth node is going to be here. What is that? Let me write directly. V4 minus V1 by 1 plus 4ix plus V4 minus V3, which is nothing but minus 7 divided by 6 equal to 0. What is Ix? Already we know. What is Ix? B1 by 2. Okay, so I can conclude one thing here. What is that? Basically, if you have more and more voltage sources connected with respect to reference node, means my solving equations will become very easy in nodal analysis. So application of nodal analysis is direct with current sources, but easy with voltage sources, because number of equations is reduced by 1. Now let us think of the same network. The same network I have taken here. Okay, in this network, okay, in the same network, let us change one more into voltage source. Okay, for example, let me think of this. Okay, here's voltage source, plus minus 1 ohm, 2 ohm, 3 volts for example. Now let us think of about this. Okay, let us try to solve this by nodal analysis. Okay, because voltage source is there. The moment it's a voltage source, we don't know how much current will flow through a voltage source, but we should be able to apply nodal analysis. How it will be, let us see. But for future reference, I need a copy of it. So let me push this. Just a minute. Okay, it will be there. Just a minute, let me think whether complete things are copied or not. So complete things are not copied. So let me try again. Yes, everything went now. Now let us try to apply KCL for this or nodal analysis for this. As usual, focus here because a voltage source is connected with respect to two non-reference nodes, because if we take this as reference node. Okay, as usual, this is V1, V2, V3, V4. Okay, you have to focus here. I don't use super node term at all. Okay, later I may tell you, okay, this is nothing but super node, that's it. Okay, now let us think of applying KCL from node 1. Okay, node 1, how much is the current leaving in this direction? V1 minus V4 by 1. So V1 minus V4 by 1 plus current leaving through this is reference node. So V1 by 2 plus V1 by 2 plus how much is the current flowing through this? Gone case, I don't know. Okay, so how much is the current flowing through this? I don't know, because current flowing through a voltage source is not known, but voltage across voltage source is known, but current is unknown for a voltage source. So how much is that? Maybe let me think of IK. So plus IK equal to 0. Okay, so this is first equation. This is first equation. Now, what is second equation? Second equation here, current leaving through this is 8Vx. So 8Vx. Current leaving through this is V2 by 5 plus V2 by 5. Current leaving through this is, I don't know again. Current leaving through this is, I don't know again. So how much is current leaving through this? Previously, one thing by KCL, whatever with the current leaving through this, compulsorily has to enter here, no? Okay, or from here current leaving is nothing but minus of entering only, no? Because KCL has to be followed. KCL has to be followed. So this is going to be minus IK equal to 0. So this is going to be the second equation. Now, can I combine those two? Yes, yes. Because if I send IK to other side, this will be there. So what is IK? IK is nothing but 8Vx plus V2 by 5. Now let us combine 1 and 2. Let us combine 1 and 2. If I combine 1 and 2, V1 minus V4 by 1 plus V1 by 2 plus IK. IK is 8Vx plus V2 by 5 equal to 0 is the combined equation we got from 1 and 2. Only one equation we got now combinedly. Getting my point, right? Now let us see this particular grand equation from where we are collecting. For example, see here, V1 minus V4 by 1. V1 minus V4 by 1, current leaving through this, plus V1 by 2, current leaving through this, plus 8Vx. Where is 8Vx? See here, current leaving through this, plus current leaving through this, plus current leaving through this, okay, plus V2 by 5, current leaving through this, equal to 0. What does it mean? What does it mean? See here, again. So current leaving through this, from the combined equation, plus current leaving through this, plus current leaving through this, plus current leaving through this, equal to 0. What does it mean? This is considered as one node combinedly is called as super node. Okay, super node is not a special thing. Simple means in writing this equation, did we know that it is super node? No, not required. Okay, we know KCL enough. Whatever with the current leaving here has to enter here, problem solved. Okay, so combined equation, very simple. See here, current leaving through this plus current leaving through this plus current leaving through this, I don't know, but I know current entering here. That entering currents are nothing but leaving currents. Problem solved. Okay, now let us continue with other nodes also. V1, V2 combinedly I got this, and after that V3, I need not write anything. V3 equal to minus 7 volts because it's a voltage source connected with the reference node. And V4 equation will not change, in the sense V4 minus V1 by 1 plus 4Ix plus V4 minus V3 by 6 equal to 0. Okay, how many equations we got? 1 and 2 nodes combinedly. Let me take it down. Now see, 1 and 2 combinedly we got one equation because voltage source is connected. 1 and 2 combinedly one equation, third node one equation, fourth node one equation. But with 3 equations, how to solve 4 variables? So one more equation should be written. Where is that? Independent of current may be of any value, but independent of current, my voltage source is known, So 3 is nothing but V1 minus V2 because it's a voltage source. So the final equation here is going to be, just a minute. Yeah, so my final equation is going to be V1 minus V2 plus is here. With respect to this is that 3 volts. So V1 minus V2 should be 3 volts. So my equation is V1 minus V2 equal to 3 volts is the fourth equation. Okay, so let us think of equations relations. Okay, previously when I have taken the first one, okay, so the first one, if you observe, just a minute dear, yes, the first one, if you observe, all are current sources only. All 4 times you are supposed to apply KCL. Okay, so four equations came here because all are current sources. It is lengthy. Now the moment you have, for example, the moment you have one voltage source connected with respect to reference, okay, the moment you have one voltage source connected with respect to reference, this is relation. What is that relation? V3 equal to minus 7 volts, one relation, remaining 3 times equation. Now for example, if I have two voltage sources, how many times you apply the KCL? For example, here once, here, this is nothing but this. Means that combinedly between 1 and 2, I'm applying, or I applied. Okay, KCL once, 1, 2, no relation. So 2 times I was supposed to apply KCL, and 2 times 2 equations I got by relation. Okay, so what is the conclusion here? If you keep on increase voltage sources, applying nodal analysis will become easy. Because the moment you got, this is called a super node. In the sense, two non-reference nodes, if you connect a voltage source, it is called a super node. Okay, so the moment you have more and more, for example, at starting, how many nodes were there? 5. Out of 5 nodes, 1 will be reference node. 4 nodal equations we tried at starting. And after that, we connected one voltage source. 3 equations, 1 relation. After that, we connect one more voltage source, 2 times KCL, 2 equations, 2 relations. What are those? V3 equal to minus 7, V1 minus V2 equal to 3 volts. So, which is better? If you have more and more voltage sources, it may be better to apply nodal analysis. Okay. Now, for example, let me keep one more voltage source, because already we stored it here, right? Yes. Okay, now let me erase this a bit. Okay, now for the future scope, let me copy it. Okay, now let us change to one more voltage source. For example, this is voltage source now, 8Vx only, but this is plus minus. This question is going to be awesome, beautiful. Okay, now how many nodes are there? 5. How many non-reference nodes will be there, or how many times you are supposed to form equations? 4. Okay, how many voltage sources are there? 3. So you are supposed to apply KCL only once. Okay, so one equation will come and 3 relations should come. First of all, let us write 3 relations first. Okay, so if I think of, as usual, V1, V2, V4, this is going to be reference. I'm not saying this as earth. Okay, so in this case, only one time KCL. Now let us try to apply KCL here, because means if I form the relation, right, V1 minus V2 equal to 3 volts, that is the relation. Reference V3 equal to minus 7 volts. Okay, relation. And V3 minus V2 equal to 8Vx relation. Now what is Vx? Vx is going to be V4 minus V1. Done. 3 relations. Only one time I am supposed to apply KCL. So the only chance is here. Okay, at V4. So let us try to apply KCL here. If I try to apply KCL here, leaving current here, V4 minus V3 by 6 plus 4ix plus V4 minus V1 by 1 equal to 0. Okay, so problem is solved or not? Yes, much simplified version. Okay, because maybe sometimes people feel that if I try to apply KCL here, leaving current plus leaving current. So focus here, leaving current plus leaving current. Okay, let me keep this. Now leaving current, Leaving current plus leaving current plus leaving current. This leaving current I don't know, but that is nothing but entering current. That entering current is nothing but these two leaving currents. This leaving current plus this leaving current. Again, this leaving current I don't know. That leaving current is nothing but this entering current. This entering current is nothing but this leaving current plus this leaving current. This leaving current I know, but this leaving current I don't know, because it is connected with reference. Getting my point, right? So focus again slowly. For example, if I try to apply KCL here, what will happen? KCL here, what will happen? For example, you know or not, V1 minus V4 by 1 plus V1 by 2, plus I don't know this current. So that leaving current is nothing but this entering current. This entering current is nothing but these two leaving currents. So this leaving current is V2 by 5. I got the leaving current plus this leaving current I don't know, but this leaving current is nothing but this entering current. This entering current is nothing but these two leaving currents. So this leaving current I know, V3 minus V4 by 6, but this leaving current I don't know. We'll end up there. Okay, so one conclusion we can make, what is that? At any cost while applying supernodal analysis or kind of stuff, okay, I don't want to highlight supernode because it is normal KCL only. Okay, for example, in applying supernodal analysis, for example, if you touch reference node, you have done a mistake. If you touch reference node while applying KCL, if you touch a reference node, gone case. Okay, now for example, let me change this. Okay, let me convert this into maybe back to 7 ohm resistance. 7 ohm resistance. It's beautiful because extended extended KCL will come. Now for example, at V1 let me try to apply. Okay, focus dear, supernode is not such a great thing, it is very common thing. Okay, so leaving current here directly let me write, because how many nodes are there? 4. Reference node 4. In that 2 voltage source are there. So 2 equations, 2 relations. What are those 2 relations? Okay, let me write the relations first. That is going to be V1 minus V2 should be equal to 3, and V3 minus V2 is going to be 8 Vx. Now how much is this Vx? Is going to be V4 minus V1. Okay, now let us see, means relations are over. Let us try to find out KCL. It's awesome. Okay, just wait. Now let me try to apply KCL here. Okay, if I try to apply KCL here, leaving current here, how much is that? V1 minus V3 by 6 plus V4 minus V3 by 6. Just a minute here. V4 minus V3 by 6 plus 4ix plus V4 minus V1 plus V4 minus V1 by 1 equal to 0. This is the one equation. Now we have to find one more equation. Now focus here, all of you please. You have to focus here. Maybe let me take KCL here. Now leaving current through this V1 minus V4. See here, V1 minus V4 by 1. Okay, V1 minus V4 by 1. After that, plus V1 by 2 plus this leaving current. I don't know. That leaving current is nothing but plus this leaving current is nothing but this entering current. This entering current is nothing but these two leaving currents, right? So this leaving current I don't know because it's a voltage source, is nothing but this entering current. This entering current is nothing but these two leaving currents. This leaving current is how much? V2 by 5 plus this leaving current I don't know, but that leaving current is nothing but this entering current. Is nothing but this entering current is nothing but these two leaving currents. Okay, so means again let me repeat. I started from here. Okay, so this leaving current plus this leaving current plus this leaving current should be 0. But this leaving current I don't know, but I know that is entering current. Now this entering current is nothing but these two leaving currents. Okay, this leaving current I know, but this leaving current I don't know. But I know that this leaving current is nothing but this entering current. Okay, so this entering current is nothing but these two leaving currents. These two leaving currents is going to be V3 by plus V3 by 7 plus V3 minus V4 by 6 equal to 0. So from where you applied, okay, so I'm sorry, yes, this is better, okay, from where and all you applied nodal analysis. Nodal analysis, if you see super nodal analysis, I think blue I can use, okay. See here, this plus this plus this plus this, this is going to be such a big super node. Now one thing I want to conclude, what is that, if you keep on increase voltage sources, means that nodal analysis will keep on easy. Now let us think of the last one, okay. After this we will start here, we will go back to previous sessions, okay. So let me convert this also into voltage source. All 4 voltage sources. For example, I think I have taken plus minus, okay, and this also let me convert into voltage source, okay. Now this is 4ix, maybe plus minus, okay. Now how many, what do you say, non-reference nodes are there? How many non-reference nodes are there? 1, 2, 3, 4, okay, 4 nodes. 4 equations are required. How many times I have to apply KCL? Not required, because I got 4 voltage sources, okay. So the moment I got 4 voltage sources, without applying KCL, I should be able to find the solution, okay. Basically, for future reference, let me consider this, because I have to work on this only. Oh, sorry. Okay, so let us think of in this particular question, what are the, because if you try to apply KCL, you will end up at the reference node. For example, if you try to apply KCL here, this current plus this current plus this current I don't know, means that you are touching the reference, okay. So anyway, let us try to apply V1, V2, V3, V4. At any cost, you should not try to applying KCL, okay. Now V1 minus V2 equal to 3 volts. Volts need not be 3. V2 minus V3 equal to 8 Vx. Now what is Vx here? V4 minus V1. So it's going to be V4 minus V1, okay. Now how much is V3 equal to minus 7 volts, okay. Volts need not be written, okay. And after that, what is V4 is connected with respect to reference node only, no. So V4 is nothing but with respect to reference node, it is 4ix, okay. Now what is ix? Where is ix? Ix is here, V1 by 2. Ix equal to V1 by 2. So if I have 5 nodes, one reference node will go 4 non-reference nodes. If I have presence of 4 voltage sources, I need not apply KCL at all. Just by relations, we are getting the answer. Now for example, let us go back and see, okay, from starting. Okay, at starting we started with all current sources. Thank God, this only, okay. We started with all current sources. The moment you start with all current sources, how much lengthy equations, it's actually difficult to solve. But the moment you keep on connect voltage sources, okay, so with non-reference node to reference node, means I need not apply KCL here, directly V3 equal to minus 7 volts. Now if I change the voltage source to one more, oh, I don't know this function, thank God it is there. Yes, it's okay, I'm sorry. Okay, so if I think of this, what's happened here? This is voltage source, this is voltage source, two voltage sources, two relations, and 2 times KCL. Now if I move this to here, okay, then what happened means I made this as a voltage source, this as a voltage source. So what happened? Analysis became easy. Now if I think of, yes, if I think of 4 voltage sources, system became so easy. So conclusion is this. What is that? In order to apply nodal analysis, more and more voltage sources should be there. Then we can apply nodal analysis in easy way. Now we'll start with, means we are going to take this particular same example. We are going to take this example because all are voltage sources only. No, the moment all are voltage sources, application of KVL is going to be direct because KVL, mesh analysis, means voltage sources. Okay, so KVL means that voltage rises or voltage drops. For a voltage source, voltage is known. So let us apply KVL for this. And let us go ahead with mesh analysis. Again, in mesh analysis, at the end, I will come back to nodal analysis first question only. Then we will be able to compare mesh and nodal very easily. Okay, we will do that in the next video. Thank you.